This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into an interactive physics simulation, the Traffic Light Reaction Time Simulator. It's a fascinating tool, and our guest is here to help us understand its applications and implications.
The simulator offers a unique way to engage students with the concept of reaction time, a crucial element in understanding kinematics and real-world safety.
Exactly. It's not just about numbers on a page, it's about experiencing the consequences of delayed reactions. How does the simulation achieve this?
It uses a simple yet effective visual representation of a car approaching a traffic light. The user's task is to hit the brakes when the light turns red, simulating a real-life driving scenario.
And the results? What kind of data does the simulation provide?
The simulation measures the user's reaction time, the braking time, and the distance traveled during both periods. This data is then displayed, allowing for a direct understanding of the relationship between reaction time and stopping distance.
So it's not just about the reaction time itself, but also the distance covered before braking. That's a critical safety aspect.
Absolutely. The simulation highlights the significant distance a vehicle can travel even with a seemingly short reaction time, especially at higher speeds. This is a powerful lesson in safe driving practices.
How is this simulation being used in educational settings?
Primarily, it's used to teach kinematics concepts in a more engaging way. Students can directly experience the impact of variables like initial velocity and friction on stopping distance.
Does it cater to different learning styles?
Yes, the visual nature of the simulation appeals to visual learners, while the interactive element engages kinesthetic learners. The qualitative data also caters to analytical learners.
The simulation is built using JavaScript and HTML5. What are the advantages of this approach?
JavaScript and HTML5 allow for easy accessibility across various platforms and devices, making it readily available to students. The open-source nature also allows for modifications and improvements by educators.
Are there any limitations to the simulation?
While it effectively demonstrates the core concepts, it simplifies some aspects of real-world driving, such as driver variability and road conditions. It's a model, not a perfect replica.
What potential improvements or expansions could be made to the simulation?
Incorporating more realistic variables, such as varying road conditions or different vehicle types, could enhance its realism. Adding scenarios with multiple vehicles would also increase complexity and engagement.
Could it be adapted for other contexts beyond driver education?
Absolutely. The core principles of reaction time and distance calculations are applicable to various fields, such as sports or even industrial safety training.
The description mentions sample learning goals. Can you elaborate on those?
The primary goal is to help students understand the relationship between reaction time, speed, and stopping distance. It also aims to foster an appreciation for the importance of safe driving practices.
Are there any specific learning outcomes that educators should look for?
Students should be able to calculate stopping distances based on reaction time and speed and understand the factors that influence these calculations. They should also be able to apply this knowledge to real-world scenarios.
The description includes a section for teachers. What kind of support does it offer?
It provides detailed instructions on how to use the simulation, including explanations of the different options and settings. It also suggests ways to integrate the simulation into lesson plans.
Are there any assessment strategies suggested for teachers?
While not explicitly stated, the data generated by the simulation provides a natural basis for assessment. Teachers can use the results to evaluate student understanding and identify areas needing further instruction.
The description mentions Java versions of the simulation. What are the differences?
The JavaScript version offers broader accessibility due to its reliance on widely available web technologies. The Java versions might offer more advanced features or functionalities, but require specific software installations.
Which version would you recommend for most educational settings?
For ease of access and deployment, the JavaScript version is generally preferable for most educational settings.
The credits list several individuals involved in the development. What roles do they play?
The credits likely reflect the collaborative effort in designing, programming, and testing the simulation. The roles might include programming, design, testing, and documentation.
And the licensing information, what does that mean for educators?
The Creative Commons license allows for free use and adaptation of the simulation for educational purposes, promoting open access and collaboration within the educational community.
The page lists other resources. What kind of supplementary materials are available?
These resources likely include additional learning materials, such as worksheets, lesson plans, or further reading on related topics. They aim to provide a comprehensive learning experience.
How can educators find and access these resources?
The website itself should provide links to these supplementary materials, allowing educators to easily integrate them into their teaching.
What is the overall impact of this simulation on physics education?
It offers a valuable tool for enhancing student engagement and understanding of complex physics concepts. Its interactive nature and accessibility make it a powerful resource for educators.
Do you see this kind of interactive simulation becoming more prevalent in the future?
Absolutely. The increasing availability of technology and the growing emphasis on active learning make interactive simulations like this increasingly valuable in education.
From a user perspective, what are the strengths and weaknesses of the simulation?
The strengths lie in its simplicity, accessibility, and engaging visual representation. Weaknesses might include the simplified nature of the model and the potential for limited feedback to the user.
How could the user experience be improved?
More detailed feedback mechanisms, perhaps incorporating hints or guidance, could enhance the learning experience. Clear visual cues and instructions could also improve usability.
So, in summary, the traffic light reaction time simulator is a valuable tool for teaching kinematics and promoting safe driving practices. Its interactive nature and accessibility make it a powerful resource for educators.
Precisely. It effectively bridges the gap between theoretical concepts and real-world applications, fostering a deeper understanding of physics principles.
That was a great discussion. Thank you for your insights.